The heavens unleashed their wrath upon Earth in a spectacular display of cosmic power. November 2025 marked a turning point in our relationship with our star, as the most ferocious solar storm of the year crashed against our planet as magnetic defenses. This wasn't merely a scientific curiosity, it was nature's reminder of our vulnerability in the face of stellar forces. The storm originated from a cluster of sunspots, each as vast as Earth itself, churning with magnetic energy on the sun's surface. These volatile regions released not one, but multiple X-class solar flares, the most powerful category known, followed by massive coronal mass ejections aimed directly at our world. The result was a G for geomagnetic storm, approaching the highest intensity on the measurement scale, rivaling even the legendary May 2020 for disturbances that had scientists scrambling to understand their implications. As charged particles collided with Earth's magnetic field, the night skies transformed into canvases of ethereal light. Auroras danced across latitudes where such phenomena are virtually unknown, painting the darkness with vibrant greens, blues, and rare crimson hues. Witnesses stood in awe, many seeing such celestial magic for the first time in their lives. Yet beneath this beauty lurked profound scientific questions. The November 2025 storm defied predictions about solar cycle behavior. Something extraordinary was happening on our star, a potential double-peaked solar maximum that contradicted established models and forced researchers to reconsider fundamental assumptions about solar physics. The drama began with active region 4274, a chaotic, magnetically complex sunspot cluster rotating across the sun's Earth-facing hemisphere. To astronomers monitoring its development, it resembled nothing less than a loaded weapon pointed directly at our planet. Their concerns proved justified when this volatile region unleashed not a single blast, but a relentless barrage, 3 powerful X-class flares in rapid succession. Understanding this event requires distinguishing between two solar phenomena often confused in popular discussion. Solar flares are intense bursts of electromagnetic radiation, brilliant flashes spanning multiple wavelengths from radio to X-rays. These energy releases rival millions of hydrogen bombs detonating simultaneously, and because they travel at light speed, they reach Earth in just over 8 minutes. Coronal mass ejection CMEs, by contrast, are physical clouds of magnetized plasma hurled into space. When the sun's magnetic fields reconfigure, these massive ejections move slower than light, taking between 15 hours and 3 days to reach Earth. While flares manifest as bright flashes, CMEs appear as enormous clouds of particles moving through the void between worlds. The November storm combined both phenomena in a devastating sequence. On November 9th, AR-427 erupted with an X-1.7 flare, launching the first CME earthward. Less than 24 hours later, an X-1.2 flare triggered a second CME. Then came the knockout blow on November 11th, a colossal X-5.1 flare, the strongest of 2025 and among the most powerful ever recorded in the space age. This final eruption sent a third, more energetic CME racing toward Earth, setting the stage for what would become a geomagnetic superstorm. The radiation from the X-5.1 flare reached us within minutes, triggering an R3 radio blackout across Africa and Europe as high-frequency communications fell silent. But this was merely the opening act of a cosmic drama about to unfold. What would happen when these massive ejections reached Earth? How would our technological infrastructure withstand such an onslaught? And what secrets about our sun's current state would this extraordinary event reveal? The extraordinary power of the November geomagnetic storm stemmed from a rare and explosive phenomenon known as a cannibal coronal mass ejection. The first two CMEs launched on November 9th, and 10th traveled at moderate speeds through interplanetary space. But the third CME, born from the X-5.1 flare on November 11th, blazed through the void at approximately 1,500 kilometers per second, over 3.3 million miles per hour. This supercharged plasma cloud overtook the earlier, slower CMEs, consuming them in a cosmic collision. The result was a single, massive, highly energized magnetic structure, a cannibal CME bearing down on Earth with unprecedented force. When this amalgamated storm finally struck our planet's magnetic field, the interaction created a spectacle both beautiful and terrifying. Earth's magnetic field acted as our first line of defense, deflecting much of the solar onslaught. The interaction created magnetic funnels where charged particles streamed toward our poles. During daylight hours, this produced the rare phenomenon of daytime auroras. At night, as magnetic field lines stretched and reconnected, solar particles cascaded along these pathways toward the poles, generating the more familiar nighttime aurora displays. While many associate auroras with green hues, this intense storm produced magnificent red glows stretching across the sky. The color variations result from different particle interactions at various altitudes. Blue and purple auroras appear when solar particles interact with molecular nitrogen, up to 100 kilometers above Earth. Green displays the most common occur when particles collide with oxygen between 100 and 300 kilometers up. The striking red auroras witnessed during this storm resulted from interactions with oxygen at even higher altitudes between 300 and 400 kilometers. For these red auroras to become visible to the naked eye, they must shine at least 10 times brighter than their green counterparts, a testament to the extraordinary energy of this November storm. Observers across unprecedented latitudes witnessed these crimson curtains rippling across the night sky, a haunting reminder of the sun's power. Yet the storm's most serious impacts remained largely invisible to casual observers. While officially classified as a G for geomagnetic storm, some regions experienced far more intense effects. The British Geological Survey reported parts of the UK reaching a K index of 9, the highest possible reading on the local geomagnetic activity scale, corresponding to a G5 extreme event. Such intensity can disrupt power grids, interfere with satellite operations, and compromise navigation and communication systems worldwide. Perhaps most alarming to scientists was the storm's rarest effect, a ground-level event GLE. Unlike typical geomagnetic disturbances, a GLE represents a direct radiation event, occurring only once or twice per solar cycle. These particles slam directly into our atmosphere, colliding with molecules and generating cascades of secondary particles, including neutrons detected by ground-based monitors. GLEs pose direct hazards to satellites, astronauts, and even airline passengers. High-energy solar particles can damage satellite electronics, causing malfunctions or permanent damage. For aircraft flying polar routes, where Earth's magnetic protection is weakest, radiation levels during a GLE can exceed safety thresholds, endangering passengers and crew. What makes this November 2025 superstorm particularly shocking isn't merely its strength, but its timing. This eruption provides compelling evidence that our sun is defying scientific predictions about its behavior. To appreciate the significance, we must look back to 2019, when solar cycle 25 was just beginning. That year, NASA and NOAA released their official forecast, projecting a relatively weak cycle with a peak sunspot number of just 115, expected around July 2025. But our star had different plans. By 2022, the cycle was clearly outperforming expectations, with more numerous sunspots, more frequent flares, and more intense space weather activity than anticipated. October 2024 saw sunspot numbers reach 160.8, shattering the original forecast. Even before the November storm, this cycle had delivered the May 2024 G5 superstorm, the most intense in 2 decades, and an X9 flare in October 2024, the strongest of solar cycle 25 until now. In February 2025, NOAA quietly revised its official forecast, acknowledging much higher solar activity. According to both the original forecast and the revised October 2024 peak, the sun should now be in its declining phase. Instead, it just produced one of the strongest flares of the space age, and a geomagnetic storm that lit up skies worldwide. What could explain this unexpected solar behavior, and what might it mean for Earth in the coming months? The November superstorm points to a startling possibility. The peak of solar cycle 25 may not be behind us at all. Growing evidence suggests we're witnessing a rare phenomenon known as a double-peaked solar maximum, where solar activity surges again after a brief decline. This pattern defies conventional understanding of solar cycles and raises profound questions about our star's inner workings. By March 2025, scientists were already speculating about a potential second peak forming. The first maximum in October 2024 was dominated by activity from the sun's southern hemisphere. The November 2025 G4 superstorm, driven by the X5.1 flare, may mark the northern hemisphere's delayed maximum, not an anomaly, but part of a second crest in solar cycle 25. This revelation leads to 3 critical conclusions spanning different time scales. In the immediate term, the storm isn't over. The G4 disturbance that began on November 12th continues, prolonged by the arrival of the third, fastest CME. NOAA confirms that G3 and G4 storm conditions are expected to persist, maintaining threats to satellites, ground-based electrical systems, and global communications. Looking to the medium term, the source region remains active. Sunspot region AR4-7 for still faces Earth and will continue to do so until approximately November 15th. But this isn't the end of its story. In roughly 2 weeks, it will re-emerge on the opposite side of the Sun. The question haunting scientists, will it have exhausted its energy, or will it return even more unstable and dangerous? The long-term outlook is most concerning of all. This storm likely represents not the end but the beginning of a second solar peak. The October 2020 for maximum was merely Phase 1. The November event signals Phase 2. We could face another 12 to 24 months of elevated solar activity, bringing more auroras, yes, but also sustained risks to our technological infrastructure, from satellites to power grids to communication networks. The implications extend beyond scientific curiosity. Our modern civilization depends on technologies vulnerable to solar storms. Power grids can experience surges from geomagnetically induced currents, potentially causing widespread blackouts. Satellites essential for communication, navigation, and weather forecasting face radiation damage and orbital decay from atmospheric expansion. During intense solar activity, even ground-based communications can fail when the ionosphere becomes disturbed. For space agencies planning missions beyond Earth's protective magnetosphere, this double peak presents additional challenges. Astronauts traveling to the Moon or Mars would face increased radiation exposure. During this extended period of solar volatility, mission planners must now reconsider timelines and radiation shielding requirements in light of the Sun's unexpected behavior. Perhaps most profound are the questions this event raises about our understanding of solar physics. Why did established models fail to predict this double peak? What mechanisms within the Sun drive this unusual pattern? The answers could revolutionize our comprehension of stellar dynamics and improve our ability to forecast space weather, a capability increasingly vital to our technology-dependent society. As we witness this cosmic drama unfold, we're reminded of humanity's place in the solar system. Despite our technological achievements, we remain subject to the rhythms and outbursts of our star. The November 2025 storm serves as both a spectacular natural phenomenon and a humbling reminder of forces beyond our control. What new discoveries might emerge from this unexpected solar behavior? What technological safeguards must we develop to protect our infrastructure? And what other secrets might our Sun be hiding, waiting to reveal themselves in future eruptions? The answers lie in continued observation, improved modeling, and perhaps most importantly, the recognition that our relationship with our star remains one of student to teacher, with many lessons yet to learn.